I'm Mikael Kalms, and I spent the past 20 or so years making games, and that's been a lot in assembly language and C++. But since about a year, maybe a little more than a year, me and the team have begun working in Unity. I'm here to talk with you today about some effective strategies for managing growth in your project and approaching this as a programmer, not as a project manager. You run into different kinds of problems depending on the size of your project and your team. If you're just a single person making the stew, then you'll be wrestling with your lines of code. What goes where? Is this going to be inside of this if statement? Am I going to shuffle it into a separate function or whatnot? Once you get up to 3 people on the project, suddenly you will have architectural problems to tackle in addition to the niggly bits. And if you ever get to 10 plus people, then you see that it's no longer just about the architecture. It unfortunately goes broader than just the code. It becomes a question of building automation that helps not just you and other programmers, but everybody else on the team to work effectively. By the way, I should give shout out to my lovely girlfriend who's been drawing this picture and the other ones. I can't draw at all, and I very much appreciate it. Thank you, darling. Now, let's look a bit at techniques for organizing lines of code. I find it interesting that even after these 20 years of programming, I'm still interested in how to organize individual lines of code. I hope that you too will share this joy once you reach my age. Let's say that you start with a program that has a reasonable structure. It makes sense. It's well organized. Now you start modifying it, adding features and changing what's in there. It becomes a bit messy. You might recognize this. Once you've done enough modifications to it, you just get this feeling, okay, this isn't quite working out. Then a good strategy then is often to take a step back, untangle the mess, break it down into slightly smaller pieces, and once you have the individual bits straightened out, put all of it together, and now you again have a program that is well organized, but slightly larger than what you had from the beginning. This cycle keeps repeating over and over and over again as you build the program. What's important is to make sure that you continue doing this cleaning over and over again. And this organizing lines of code part is really about finding strategies for going from the tangled mess to a couple of smaller non-tangled bits of code. To demonstrate this first part, I've created a Pong game. You will be amazed. This is our demo project. Thank you. Now, if we look at what's inside of this game, we have 2 pedals, 2 walls, which are located at the top and the bottom, and a pair of, and then also, there we go, walls on the side, and a slight bit of game logic which didn't quite fit into any of the visual bits, and then the scoring display. For each of these, if we dig around, then we can find a little paddle script, for example, on the paddle. On the vertical walls, you find a similar, there's a wall script on this thing. Now, the principles that are at work in the design there is that one thing in the game is going to be one prefab, and if we needed custom logic for one of these things, then we create one MonoBehaviour. And the entire application, it's one scene which contains a collection of these prefabs, which have links between each other. And this is a perfectly reasonable structure for this project. However, when this project grows, the structure will also need to change. So what we'll do now is we're going to look at this a bit more in detail and see which are the strategies that we can use to even organize this tiny project a bit more. The first thing that struck me when I was looking at this game, after I just made it work, was confusion about instances, prefabs, and scriptable objects. When I looked at one of these paddles in the inspector, I could see this. Okay, I have 3 parameters on, let's say, the left player's paddle. I can change a couple of things in there. Now, does it make sense for me to change the input axis on the left paddle by changing it on the instance, or should I be doing that in the prefab? Well, I presume that the input axis is different for both players, so it probably should be changed on the instance. What about movement speed scale? Is that something I should be changing on the instance or on the prefab? Nothing in here, in this view, gives me an indication of what the underlying code expects of me. So let's drop down and look at the code that represents that prefab. Okay, there we have them, 3 variables, which happen to serve different purposes. The intention here is you ought to change one of these for each player, but some of these parameters should really be shared for both players. So here's a strategy that I like to use, which is saying, like, if you're going to have something only once in your entire game, you know what? Create a prefab and then instantiate it into the game. And if there's something where you want to have multiples of it with some instance-specific modifications, yeah, okay, create a prefab and instantiate it and override a couple of settings. However, maybe you don't want to expose all the flexibility in the world to whoever is modifying the prefabs. Then make the decision, like be bold and make the decision to reduce choice by saying, okay, these settings which are supposed to be shared, move them out of the prefab, put them into a separate scriptable object, and then have the prefab refer to that scriptable object instead. If we do that with the shared settings, then, okay, there were 2 settings in the paddle which we wanted to have joint for both paddles. Let's move them to a scriptable object, and instead we just have a reference to that paddle data in our paddle component. What we end up with now in the inspector is 2 things. There's going to be paddle data inside of, like, lying there as an asset, and then for an individual paddle, then you'll see that, okay, if you click on that in the inspector, then you'll see, okay, I can change the axis name, and I can change which packet of shared settings I'm pointing to. But I'm probably going to leave it pointing to the default one. At this point, if I don't know the game, I see much more of the intention behind the settings. Another thing then that comes later on if you were working on this game is you'll notice that the MonoBehaviours, the individual ones, they will grow larger and larger and larger. So we're going to try splitting up the existing MonoBehaviours in this game. this is a principle that we'll be using. It's called the single responsibility principle. And the basis of this is we're saying that each class is only going to handle a single thing. And if we do a good job of finding what this thing is, then we'll be able to describe in one or a few sentences what this class does. And whoever hears this will understand both, this is what the class does, and equally importantly, this is what the class doesn't do. If you can manage to find a brief description which narrows it down like that, then people will have a much better grasp of what the individual classes do. It's a fantastic principle. You can use it when you're working on a code base of an arbitrary size. So, is this legible for people at the back? A bit of yes or no? I'll go with that. So here is a piece of perfectly reasonable code for a paddle. Now, okay, we have some references to data up at the top, and it seems like it does all the things that we need to manage a paddle. However, if we look a step closer, then we could see that there are different kinds of parameters involved there. This thing finds other components. It handles inputs. It has a tiny simulation model for the paddle, and it also triggers audio. So if we wanted to, there's an opportunity to break things up here into smaller bits and pieces. Here's a ball. We could say, okay, this is just the ball. And this handles ball things. Or if we look slightly closer, then we find that the ball has a velocity, which is both being used as for the designer to control what's the initial velocity vector of the ball. It's also being used by the physics, like by the homemade physics simulation, to keep track of what the current velocity is. So as soon as the ball starts moving, we lose information about the initial velocity since we're reusing that variable for two slightly different purposes. We have our homemade physics simulation, which is not just the movement up there. It's also the reaction when you're hitting a ball. I would consider that to be part of the simulation of the ball itself. And in the middle of this on trigger enter, it's deleting its own game object. Now this thing, a piece of code that deletes the owner of itself, is not something that you see very commonly in large code bases. People tend to delete things. People tend to have owners delete things that they own. So we've seen a lot of different types of responsibilities in these classes if we're looking really closely. We've got game logic, input handling, physics, simulations, presentations, and various other things. Now, we don't need to have all of this in MonoBehaviours. The first couple of things there, we could very well put these into other MonoBehaviours. We can move it over into ScriptableObjects. We could even have it in raw C# classes if we wanted to. The parameters that we're exposing for tweaking, they will either need to reside in MonoBehaviours, or we could move them over to ScriptableObjects, just like we did with the shared parameters. So there's only that last little set there of things which really must reside within MonoBehaviours. Now, I believe that for many games, it's worthwhile to aim for getting as much as possible of the code out of the MonoBehaviours. So this is a point where we need to make a choice. Either we move things into ScriptableObjects or we move things into raw C# classes. Now, there's a bunch of great presentations on ScriptableObjects already from previous Unites. What you get when you're starting moving code into ScriptableObject is that the Unity editor understands what you've done. You can use the Unity editor to inspect what's going on inside of these ScriptableObjects. It's fantastic. It might be the right choice for you. I, however, prefer moving to regular C# classes. I think that that is based on how you have slightly more of the C# language available to you at that point. And I'm very fond of the idea that the code that you're writing can be moved, at least a large portion of it, outside of Unity. It can move it into a regular .NET program. Do you need to run this in a backend, on a backend server? Maybe you want to not run it as a headless Unity client, but as a raw .NET application. What you're losing out if you're going for regular C# classes is that the Unity editor will no longer understand what you're doing. So it will be work where you'll need logging and using the debugger and so on to inspect what's going on there. Me being a seasoned non-Unity programmer, I'm perfectly comfortable making this choice. And since everybody else seems to be talking about how do I stuff things into scriptable objects, I was thinking, okay, this session I'll demonstrate what happens when you use raw C# classes instead, just to present a counterpoint. So the principles that will apply is to try splitting logic up in depending on the type of responsibility there. And anything that's in MonoBehaviours that doesn't need to be there, we'll shuffle it over into regular C# classes. So what happens with a ball, which used to have a little physics simulation and a bit of logic checking, okay, did I hit a horizontal wall, did I hit a vertical wall, and so on? Well, that little physics simulation, we can move that over into a class which we call ball simulation. The only job that one has is to do physics integration and then react whenever it hits something. Then again, does it make sense for a ball simulation to make decisions based on what it actually hits? That's more game logic level to me. So what we end up with here is we're going to have the ball, which has a logic portion. The logic portion controls the simulation in some ways. And then the result of the simulation is something that needs to feed back into the MonoBehavior. The only bits bits that are outside then in the MonoBehavior you see is create these objects, tie them together, and oh yeah, that destroy operation, it's no longer deep down into 3 if statements. The destroy operation will be still remain in the MonoBehavior, so we don't have it hidden many layers down. These are the only clear the clear areas of responsibility left in the MonoBehavior at this point. There are more things that we can do to this, however. We see that it's kind of difficult for, in this case, if you look at the ball simulation there, where it updates its position, apparently this code needs to send in a position and then it returns a new position from there. So the ball simulation doesn't really own the ball's location. It just does things to a ball location which it is being given and then returns it out. So it's not perfect the way that things are tied together here. So if we work with interfaces, maybe we can share a portion of that ball MonoBehavior with the simulation. Not all of the MonoBehavior, just the bits that it needs. So we're doing some more changes here. What we're doing here is we're saying, okay, this ball here is going to have a little interface on it. This local position adapter makes it possible to hand the reference to this ball object over to another class, but you don't give it the entire ball class. You just give it the local position adapter aspect of it. So now ball logic itself can only access the position of the MonoBehavior, but it can access it directly. Similarly, the ball logic, it doesn't necessarily need to return a flag which is saying like, is it time to destroy or not? You can very well introduce a delegate there, which is what's happening at the last marked line there. So the ball logic can call a function, it just doesn't know which one. And that's effectively a function call outwards back to the MonoBehaviour. So what we end up with now, which is pretty neat, is that we have all this setup code and the interfaces and so on, but what's happening through every tick after that is just drive the logic. And that's it. And by the way, the logic will be driving this simulation. That's why you don't see that around there. Now, if you use those previous principles, then you can take it pretty far. And you'll be fine on a one-person project. Now, let's go slightly more abstract and think a little bit about software architecture and the problems that you encounter on slightly larger projects. This is so situation dependent that I'm not necessarily going to show you examples of here is how you do it. What's more important is being aware of what you have in your toolbox, and then as the need arises, pick the right thing for the job. One thing, however, is appearing a lot since we happen to be making specific games. If our game is just MonoBehaviours, then we have things that talk with other things. And there is no hierarchy to speak of. But once we start introducing more specific, more fine-grained classes into this one, like having like a ball logic and ball simulation, perhaps objects that deal specifically with input, then we should be able to construct some sort of hierarchy here. We have the MonoBehaviours, which have to know about everything else, because what do? They just wrap up all that other logic. But then simulation pieces of the game, they don't necessarily need to know a lot about how the logic works. They should just run a simulation, and then sometimes logic feeds in signals to it, and then the simulation reacts accordingly. Input mechanisms, they should really... It shouldn't be a case of someone checks, did I press the W button somewhere deep down within code? Rather, input should be something that happens in a self-contained place where to figure out, are input events being generated, capture those events, and then feed that into logic, who then decides what's going to happen depending on what the user just did. You can often create a pretty nice hierarchy of this kind. The part where it tends to break down is anything that has to do with presentation. That is logic that is there to spawn special effects, anything that updates your HUD, anything like updating scoring counters, etc., etc. Somehow that presentation needs to know what's going on in other systems. But that doesn't necessarily mean that it's a good idea to say that presentation has access to everything. If you can, see if you can find a way to separate logic and presentation. In an ideal world, it should be possible to run your game logic without any presentation being existing in your game. You should effectively be able to run it in run your code base in two modes, logic only and logic plus presentation. If you make a separation like this, what you end up doing is you get to focus the logic bit of the code. It becomes pure logic, presentation becomes pure presentation, and then you have some niggly bits to figure out when it comes to actually connecting these so that presentation is updated at the right times. But what you get is you get a pretty natural boundary between the two parts, and it will reduce the overall complexity of the game that you're building. The only thing which logic tends to run into is that sometimes it needs to wait for a presentation to catch up. Sometimes you have a thing which is really a collection of data. This thing here, this object that you created, this class, it doesn't really do anything. All it does is it contains things. It's perfectly fine to create those sorts of classes. You don't need to mash in all the logic, all the operations that can be done with that data into that same class. It's also perfectly fine to create classes which don't really own any data. A class which contains a bunch of functions whose only purpose is to manipulate other objects which are being given to it. For instance, you could very well have an object which is where when you create it, you give it another object as a constructor parameter, and then what this helper class will do is it will be manipulating this object without actually owning it. It's a perfectly fine way of designing certain systems. You can also find static methods useful. What's really nice about creating static methods is that if we presume that it doesn't touch any global variables, then you can look at a call to a static method and see, okay, these are the things that are being passed in, and therefore I know which things that this method could possibly touch. So I don't need to go scouting around. I don't need to look at the implementation of this method to know the things that it clearly couldn't possibly be affecting. And this ends you up in the field of functional programming, which is effectively you're doing applied maths. I send in things to a function, the function returns a result, or maybe modifies one of the output, one of the out parameters. But let's say you just send things in and then returns a result. This kind of programming, at the end of the day, if you're trying this approach, then you will find that you get less bugs than if you write regular, stateful, typical object-oriented programming. Now, you don't need to take my opinion for that. Take John Carmack's instead. Another thing that's really good to have in your toolbox is an awareness that you can decouple objects by putting other things in between them. Sometimes you're sitting there thinking, okay, I have a, let's say, like if we're going back to the Pong example, I have the ball logic here, and then I have a score presentation here. Is the ball logic going to inform the score presentation when something happens with regards to the ball? Is the score logic going to query the ball logic? One of these two is going to need to talk to the other one somehow. Okay, maybe we should put something in between the two. Maybe we're going to create a buffer object whose sole purpose is this is a place where the logic can write things and then the presentation can read things from there. Maybe we should put a queue in between so that all the different logic systems can post things into this queue, and then the presentation side is going to sit there and read what's been happening from that queue. Maybe our game is turning so big that it makes sense to have a message bus in there. Now, this message bus here is something that it's a double-edged sword. But the core principle when you're doing messaging is that neither receiver nor sender knows about the other party. Rather, both of these know that there is a message system. So in our example, the scoring presentation, that one is going to subscribe and say, OK, I want to know about any events that have to do with scoring changing. And then the game logic, then in various places, it's going to post events to the messaging system with events that indicate, OK, it's like this player gained a point. And this kind of thing is really, really good for decoupling logic from presentation. Since all that you need in order to get this running is then you need a global message system and you need a way to describe messages of different types. Unity has the unit events, or if you want to write your own thing in order to get a little bit more type safety in certain places, then there's an example implementation down there at the end of that link. Something that I struggled a lot with, which I consider to be on the architectural side, that's how to organize scene loading in a project. I wasn't at all comfortable with Unity's model of handling scenes. And it took a lot of work until I ended up in a place where I could, where I could rest easily at night. The first thing that we had to do was to stop using LoadScene mode single. The very idea of I'm going to load a scene and therefore I'm throwing out whatever currently happens to be loaded, I consider that to be a short-sighted model. So we've moved over to purely doing additive load operations instead, and doing explicit unloads for scenes whenever it's time to get rid of something. I'm not comfortable with DontDestroyOnLoad flagging things either. This is kind of get out of jail free thing, which I suspect was introduced because LoadScene mode single existed. So if we're loading things additively and we're unloading, then there is no longer any reason to be using the DontDestroyOnLoad flagging. Instead, you could have certain scenes that live for a very long time in your application. And then you have a model where scene is loaded, objects get created, scene is unloaded, objects get destroyed, rather than in a couple of places I create objects which are DontDestroyOnLoad flagged, and then a while later I start destroying game objects explicitly, not removing that flag, but actually destroying them because there is no DontDestroyOnLoad flagging mechanism. Another thing which made a difference to us was going for a minimal boot scene. This is what's being loaded when our game starts. And boot there is just a script which tells the scene group loader to load a couple of other scenes. And the reason why we have this in here is to reduce the amount of time it takes between application startup and us getting control of the things. We want to be able to show a loading screen pretty early on. Another thing that we found useful, not yet in our current project, because we're not quite there yet, but which has been immensely useful on every single other game I worked on, has been supporting a clean and controlled shutdown. So if your game has it often has a very particular order in which it creates things at startup. And in the same way, you should have a very particular order through which you shut things down, because it's a great way of finding errors. And it gives you opportunities for finding out if you're leaking things. For example, if you have this minimal boot scene, imagine that you'd start your game, it loads the boot scene, and then it loads all the other scenes. You run your game, and now you click quit, and you unload all scenes except boot. At this point, you should have next to nothing resident in your application, right? That's a perfect place to check, do I have memory leaks or not throughout an entire application, like throughout my entire application lifecycle. Besides, when you're exiting play mode, then Unity editor won't do a full domain reload. So this makes the editor and any kind of like edit mode scripting that you have less likely to show weird behaviors after you've run your game in the editor. So here's an example of our game's scene layout. Boot there is going to load in static and game. And static, that's all these things which we used to have DontDestroyOnLoad flagged. I don't care about which order the things in static, the order in which they are being shut down particularly. Game, on the other hand, represents things that should be alive throughout the lifetime of my game. And this is things that I normally wouldn't DontDestroyOnLoad flag. And game, in turn, you see that game state switcher? That's an ugly bit of glue which you can ask to, okay, please load in all the main menu things, or please unload all the main menu things and load the in-game bits and pieces instead. Another thing which we used to be having problems with was scene files and merging. I presume every single Unity developer has felt the pain. We started out saying, okay, we're going to use a real version control system for our game. Excellent. Store all assets as text. Excellent. Prefabs is not just a tool for reusing content and making variations of it. We're using prefabs explicitly as a way of getting data out of those large scene files. Even things which exist only once in our game, we create prefabs of them, with the sole purpose of making sure that the detailed structure of these things are stored in separate files in our version control system. That didn't do everything, so we still had problems with large scenes. So then we started splitting certain scenes, in particular in-game, into multiple smaller ones. So we have ended up with, when we're in-game, we have an environment scene for the current level. We have a logic scene where we have like most of our custom MonoBehaviours. And there's also an in-game 2D HUD scene. And there are 0 references between these. And it took some extra tooling, but we found that it was worth it splitting it like that. Now, if we look at even bigger teams, 10, 15 people, then we also need to do some work on the process automation side. The core of the process automation here is that you want to be doing, as a programmer, you want to be doing like the twiddly bits. You want to be doing careful work that is unique in its nature. And you want to leave as much as you can of the repetitive work to the automated dumb things. The first thing that you should give a try is writing tests for your code. If you're moving things out of MonoBehaviours and into regular classes, in particular, then it's fairly straightforward to use Unity's unit framework for building unit tests for both logic and simulation. Doesn't make sense everywhere, but if you build a pool like this, then what tends to happen is that half a year down the line, another programmer isn't so afraid to touch your code. But it's not just about testing code. You also want to test more of your content. And this is not so much about you. If you have content creators on your team, you would prefer that they tested their content. And by default, they have one way of testing content. That's start the game and check whether or not the game works and how it behaves. Now, every time that someone, let's say a content creator, can find a problem before they start the game, that's a tiny bit of time that you have saved. So if you can create test logic that content creators can trigger, like validating, let's say, validating a prefab or validating some data which they've input through a custom editor or something like that. If they can just click a button in the editor and have a quick validation around there, then they will save time. They will appreciate that you've helped them save time. And the next step after that is hook it up so that Unity test runner will also run these things. So you then get automatic retesting of these things on a regular basis. But who's going to be running the Unity test runner then? Your build system does that. This here is a screenshot of our local Jenkins deployment. What's happening here is that every single time that we commit something to source control, then this gets started. And given the timings on one of these lines, it looks like it takes about 10 or so minutes, and then we have a completed build. And you see that test step in there? It means that not only did it do a build, but it also ran all the tests for us. And if you're putting in some extra effort in setting this thing up, then you can make it so that it starts notifying people over Slack or sending emails whenever there's a problem and they've checked something in. So with that feedback loop closed, what happens is that people who didn't particularly care about breaking the build suddenly becomes very interested in stop getting these Slack notifications. And therefore, the build gets broken, and then it magically gets fixed. And the master build engineer person often doesn't even need to get involved. Another thing that has been really valuable for us, and probably is for you as well, is the creating automated playthroughs. This is about making some kind of AI that can play your game. It doesn't need to be smart. In fact, for our game, the first AI that we made was called the Random Action AI. It would roll the dice every time that it needed to do something. And what we would do is we started up 6 or 10 of these game clients on the same box with like tiniest possible window, lowest detail settings, and then we just let all of these run, and we could watch them crash left, right, and center, and then look at the logs. Every time one of these crashed was one moment where we encountered a bug without somebody actually needing to play the game to find that bug. So every error that we found there is an error we didn't need to spend time finding. So our playtest became more about checking, okay, is the game fun? Is the game balance good? Are there particular visual glitches? That sort of thing. And whereas the AI would find a lot of the really stupid mistakes ahead of time. Now, there's a whole bunch more things that you can do on the process automation side outside of this. I'm not going to go into detail there, but the one big thing, I think, is imagining that this is not 15 people creating a game. Imagine that it's 15 people who are creating a live service. By the way, the service is already live. The first users of this service happen to be the developers themselves. And the Unity editor and that experience is part of the service. How do you find out about the experience of these users? You start putting in instrumentation of extra logging, telemetry, and things like that. But not for the purpose of understanding those external, the experience of the external people there, but for understanding the experience of the developers themselves. If you start working like that, then you're thinking web dev And you'll see that there's a gazillion different tools and things and ideas out there which you can bring over into classic games development as well. Now, we don't have time for questions, unfortunately, but if you want to talk more about software architecture, any of these things, then I'll probably be around somewhere out there for the next hour or two, depending on how many curious people happen to stop by. Thank you, everybody.